Okay, let's begin our lab session. This is going to replace our class meeting in the 13th week, the first class meeting. We're going to look at the same model we've been working with. Kaiser and Messer has this sort of detailed crop model in Chapter 4, and we looked at already what would happen if we wanted to really investigate the potential for selling labor off the farm. So we're going to back away from that example and build their exact model to get an idea of what parametric programming looks like and sort of how to build one of these bigger models in both the spreadsheet and in GAMS. So that's our topic. And so let's start just by looking at what they have for this larger disaggregated model. I guess disaggregate in terms of the stages of production is probably the best way to talk about it. We've looked at corn versus soybeans versus wheat over and over in several different ways of thinking about things, but the real sort of nuance to this model is that they have the plowing followed by the disking, followed by the planting options, and then when you finish planting, you move over to harvest, and then once you've harvested a crop, you can choose to sell it at harvest, and that's as far as it goes. There are no marketing options beyond sale at harvest in their setup. Okay, so yeah, I just want to make sure that you note that the most recent version of this we used in class added that sort of family labor and trying to link or delink that, and that was really a sort of side route that we took to be sure that we understood what substitution possibilities in linear programming are and what we are implying when we build a model where hired labor substitutes directly with the family labor or the labor allotment that we are given. Okay, so the one thing we haven't looked at in terms of building the model is the idea of separating all cost items from revenue items, and that's what's done and nicely sort of demonstrated in Chapter 4. So you plow, you disc, you plant, you harvest, you have an opportunity to hire labor. So this is the cost side of the model. And then over here we have the returns activities. So you can take that harvested corn and sell it, take the harvested soybean and sell it, harvested wheat and sell it. And the returns are listed on bushel basis. Okay, so this is the price per bushel, the return per bushel. The harvest is done on an acre basis, so you harvest an acre down here of corn that's been planted, disked, and plowed. And so if you track this back, right, you could track it all the way back and see that it's been plowed, then passed over to planting corn, then passed over to harvest of corn. And so you need another one of these negative positive relationships, and you move up here, and that's what this is. This is a balance equation or a transfer equation. You'll see me call them transfer equations. You transform the 1 acre of harvested corn into 135 bushels of corn in other units, right? So you transfer from units of acres to bushels. And then you sell them off 1 bushel at a time with a return of $2.60. Okay, and so we have zeros over here, recognizing these are transfer rows. You can't sell a bushel until it's been transferred from the harvest activity right here. And harvesting 1 acre gives you 135 bushels, so you repeat this activity 135 times to sell off all of that. Okay, the nice thing about this is it incorporates the crop pricing 260 versus 635 versus 370 directly into the LP model. We don't have to deal with thinking about things in gross margin terms. So the budget analysis gives us gross margins to compare across crops, but they are dependent on the price assumptions, and so as modelers we need to get those price assumptions directly into the model. Okay, if we were going to build this in a spreadsheet, there would be no reason to deviate from this Tableau setup that they have. They have activities in the columns, they have equations or constraints making up all the rows, and so we could do that exactly the same as they've set it up, just do a direct copy over into the way we've been setting up spreadsheet models. So activities get the columns, and these are in some sense variables, but the sort of tradition in linear programming, especially these kind of large models that have a fairly broad view of the stages of production and so forth, is just to say this is the activity set. Okay, so we got this set of activities listed here using the same exact nomenclature from Chapter 4. We have the objective coefficients, that first row that they gave us in the Tableau, and then down here we have the empty cells, the variable level cells that we would leave blank or leave as zeros in Excel to let the solver algorithm make adjustments to these. And so you see the base solution that we've had numerous times. We're going to plow 600 acres, disc 600 acres, and then when we get to the next stage of planting, we're going to split that out between corn and soybeans. We're going to harvest all the corn and soybeans and then transfer those to marketing activities. So this Tableau setup is nice. It tells you that those 354 acres are going to give you 47,813 bushels of corn and 11,000 bushels of soybeans. So you get the actual production amount there. Okay, so just a couple of notes on here. You see that there's lots of pieces right there. This equation for land really only has 3 non-zeros. The labor equation is really the key part. Excuse me. The sort of cross-activity information here, because every activity except for the sales activity uses some labor, and so this breaks it out by stages of production. So the stages really relate to labor. The rest here is transfer activity or just a limit on labor. Okay, so that's why we have this one limit that says we can only hire up to 900 hours of labor, and that it directly substitutes. It's a homogeneous good, right? Labor is, whether it's family or hired. And then everything else, besides that one, is just a sort of transfer balance. And you see that I've called these transfer rows. Okay, so I just wanted to be able, they're all kind of, the plow and the disc is just the balance for land. And then for these, it's just a matter of, these are the transfer to get corn into bushels units, and these are transfers to get planted corn into harvest corn, right? So the units aren't transferring here. It's just the stage of production. So any kind of naming convention, I was trained to call these XFERs and then come up with something useful for a subscript or parentheses term. You see, I've not been too consistent with my parentheses. I left them out there. But however you feel comfortable naming these things, they have to be distinct. And you have to be able to put together a sort of consistent table that would let someone understand from the naming as much as possible. The other thing to note here, the Excel will read these empty cells as zeros, all right? So you don't have to worry about going through and filling in everything with a zero first. And then, as modelers, as sort of math programmers, we should be able to make the connections and say that every activity here is going to be connected to a constraint either through directly, right? So all of these activities up to harvesting wheat, I guess even hired labor, through harvesting wheat are directly related to this labor constraint. So we know that no matter what we do, the sum product here will never get bigger than 1,700. Right, so the plans up here under all these activities will be limited by labor. The one sort of connection to this is there's a hired labor activity that could cause us to expand this constraint, but they're linked together through this column, through the hired labor column. And so the extended sort of labor constraint would say either family labor or hired labor. In terms of the other activities, let's think about maybe harvest activities or plant activities. The planting activities are directly constrained by the 600 acres of available crop land. Okay, so these activities are the planting activities. They all have ones, and that 600 imposes a limit. So to get to the idea that harvested acreage is also constrained by the available land, we need to track the indirect relationship. Okay, so these are the transfers that take harvested land from planted land. So if you plant something to crop, it generates a -1 in the transfer row, which allows you to then use it to harvest corn. The -1 in the soybean harvest transfer allows you to harvest 1 acre of soybeans. So that's the indirect relationship. So if you want to track the constraints on harvest activities, you track it backwards, 1 to -1 up to this row, and that's where you see that the 600 acres are also going to bound how much acreage we're allowed to harvest. Okay, so here we go. Planting, directly constrained. Harvest, indirectly constrained. If you want to look at how marketing, the sale of crop bushels are indirectly constrained by the land constraint, you have to go through 2 steps. The first step, the bushels that are available to sell are linked to the harvest of bushel or of acres, and so that first transfer set, the transfer crop bushel constraints, would work to do that. And then the second step would be to then repeat this right here. The harvest is linked back to the planting, and the planting is directly constrained. So you can make the case that everything here is constrained by either the acreage or the labor, or both. And so we would, how would you could keep going and say on the other side of the model, if planting activities are directly constrained, then plowing and disking must also be indirectly constrained. And question 1 of your assignment asks you to sort of explain that. Okay, so I built this in Excel. Let me pull that up. Okay, so we have the spreadsheet model here in its base form. You have this exact spreadsheet. I believe it's called Chapter 4.xlsx. Anyway, it's posted with this assignment, or this lab video. And you see here I've left out everything. This is the exact replication. These are all sum product formulas, and I've set these all up. These are all less than or equal to constraints, so that's fine. And so it's a fairly straightforward. If we open Solver, I know it's small on your screen, but you can see we've got an objective variable, maximize, changing the entire row of activities, and then all the constraints are the same type with non-negativity constraints there, and Simplex will solve this. I'm not going to solve it. I want to show the linkages a little bit here. Okay, so I want to walk through these linkages that these indirect linkages, and sort of see how we might use the spreadsheet to help us, help us understand these. We have all the formulas here. Everything is set up, and I'm a big advocate of building simultaneously in a spreadsheet and doing coding because you learn so much being able to see these formulas adjust. So I'm going to show you what I do. So let's say I wanted to sell a bushel of corn. So you put a 1 there. The objective variable goes to 2.6, but we have a constraint violated. Okay, so this can't hold, and so we would have to track from here over to here and see that, oh yeah, we didn't provide that bushel of corn that we want to sell. It didn't come from anywhere, right? So we've got a violation, so we could put a 1 there, and now we've got, everything is okay up here, but we might as well go ahead and set this to 135, right? Because we can balance that off. If we're going to harvest the full acre of corn, we might as well sell it all, and then we get $251 for that. And so we track back through our constraints. This one's fine, it's less than 1,700, but here we have a constraint violation. How do we fix that? Well, we have a 1 coming from right here, And the negative one over here is what we need to balance it off. So that means we have no way of, we're harvesting an acre of corn that we don't have. It needs to be planted first. That's what that negative one is telling us. So we need to add planting of corn. Okay, we add the planting of corn. We take on a little bit more labor, take on a little bit more cost, so we lose up here in the objective variable. It goes down. And we also generated a new violation of our constraint, right? So these constraints are fine, but this one isn't. And so if you track here, you see that you're now planting an acre of corn that wasn't ready to be planted. It was not something that we could do because this negative one is sitting here telling us the disking had to happen first, so you add the one there. It brings down the objective variable, right, the gross margin, by a little bit more, and we generate a new constraint violation yet again. And so here we have the one violating this less than or equal to 0. Track it over, and you see that we needed to plow first, so you get a 1 there. Get to the end, we have the gross margin for corn, 171. Read down through here. Every constraint is okay. And so we could do that for anything. If we start from one activity in the model, we can find all the linkages by going down through here and inspecting the constraints every time, because that's what Excel is going to do, right? Excel is going to quickly find all the combinations that are feasible, but as long as you maintain feasibility, as long as you go through and track, you could make a recording or come up with a valid sort of explanatory picture of how all of this works. And so it's why I sort of advocate. So the other is just the layout. For doing these in spreadsheets, the layout is nice, and you can play with punching in numbers quickly and seeing the comparison of the constraints. If you're in a coding environment, obviously there's advantages there as well, and we're going to look at those. If you're in a coding environment, this sort of single activity test requires you to actually code up that test and make it work. And it's not all laid out before you with automatic adjustment to the formulas. Yeah, so let's go back to our presentation. And let's say we solved that base version of the model with $2.60, $6.35, $3.70. I'm not sure I had all those numbers correctly put into the spreadsheet there. But I did solve that original model. So 260 versus 635 versus 370, you solve it, you get that same solution. 354 versus 245, 246. These are the bushels sold at these values. So all that budget information that we started from, comparing gross margins for corn, soybean, and wheat, is now directly incorporated into our model. It's all sitting there in the activity set. And so our sensitivity results down here are going to be range analysis directly tied to the price of the outputs. And that's the way we usually get information. It's the way we want to typically communicate information out to others. And we also get something nice. We get these range values that say a new solution, a new change in the acreage allocation, and by extension the bushel production, will be generated if the corn price falls by a penny or increases by 3 pennies per bushel. Same thing, the soybean price changes would cause that. So 2 cents or plus 7 cents. And so these are relatively small changes. The model is very sensitive to the initial price structure, corn versus soybeans. It takes large changes to get any change in wheat, so we're largely going to focus on the two corn-soybean option here. And the way we're going to do it is, the reason we're going to focus on this is to think about parametric programming. So this sensitivity information is great. It tells us that we are going to be, in short order, small changes in these prices could cause us to want to make adjustments to the plan. Well, what about if that price really does come in at 264 or 263? So we know we're going to change the plan. What's the plan going to be? That doesn't tell us this, right? This sensitivity information only tells us, we only really know that corn acreage will go up. Does it go up to the full 600? Well, we'd have to run that and test it. But we might be interested in a number of things. We might be interested in not just what happens when it goes up, but also when it falls. And if it continues to fall, is there another sort of change in the production plan? And so that's what we call parametric programming, actually generating the new solutions. What is the new acreage? What is the base acreage at 260? What's the new acreage when we get to 263? And what's the acreage when we get down to 259, I guess. And so that's what parametric programming is. It's this idea that you can iteratively build out the full sensitivity of the model to adjustments in base parameters. So if we were to change the price outside of the allowable increase, outside of the allowable decrease, and change it further from those two values if it's warranted, then we would build up a set of quantity and price pairs, the acreage planted to corn versus the price estimate for corn, that would look a lot like a supply function. And that supply function would summarize the optimal response to output choice relative to its own price. So it's a true supply function. It's just discrete. It just has these jumps. You need a threshold change in the price to cause you to change. And so it's not sort of the classic linear or curvilinear supply function, but it is a supply function. So let's just look at the example that I'm going to say here, and the one from the book. Changing the corn price to generate all potential quantity changes of corn gives us the model summary, all else constant, supply function for corn. And that all else constant is important because it assumes all the other parameters are holding their initial value, or their base value, or their best value, or their average value, just like when you draw a supply function for the market for corn. Right, so the aggregate supply function for corn in the market, when you draw it, you are building a level curve. Okay, and we're going to talk about this more when we come back for our next lecture. But it depends. That location of the supply curve assumes all else constant. It assumes nothing else is changing, because if something else changes, that's what we call a shift in the supply function. And so we'll explore that option as we move through our parametric programming example. The constraints aren't changing. Something else is adjusting, right? And so we could track. Okay. So the supply of corn is increasing with the corn price, but the constraints aren't changing. So we have to have an alternative adjustment that's going on, right? So we know we only have 600 acres. So if you tell me I'm going to expand corn acreage, then by extension I know that some other output must be falling. And so the other thing that we could track is the cross supply behavior. So as we're adjusting the corn price, how does soybean output respond? Okay, and so that's the other piece that I want to be sure that we pick up on, this that's sort of ignored in the textbook treatment of this topic. Okay, so from the sensitivity on from the Excel report here, we have our two test values. We need a 259 corn price and a 263 corn price to see how the changes would, to see what kind of changes we would get. And so we know the model is going to be sensitive. We know it's going to change, and so we could run those simulations. And so in the spreadsheet, just change your corn price to 259, hold everything else at the base value, solve it, and you get the corn quantity in acres is 0. The soybean quantity is 600. At 260, you hit the switching point, right? And so when we see that 0, we also know that it's no point in lowering the corn price, because 0 is the origin of any good supply schedule in the quantity side. So we don't need to go further below. 260, at that change, that 259 to 260 flips the model and says, now we're going to go from 0 to 354 acres of corn, and we'll lower the soybean quantity from 600 to 246. A small price increase, 3 cents, from that 260 value causes us to make another adjustment and go to the full 600 acres of corn. That 600 acres is all we have, so the soybean quantity falls by the full 246 to go to 0. So these are this is a 2-option model essentially because wheat isn't competitive. And so these are just complements to one another, with the 600 being the total. We could have anticipated this from the budget analysis. We knew the gross margins per acre were very close for soybean and corn. We knew they were going to compete for that acreage in the model. And so as the relative returns change by a little bit, we're going to get those changes. Since the model only differs, so if we're changing price, the only really other thing that is different in the model is how much labor does corn versus soybean use. They both use 1 acre when we decide to plant. And so what we see here is there's this narrow range between 260 and 262. This is figure 4.1 from the chapter 4. There's this narrow range where there's a little bit of play in the model where the family labor constraint has some effect. Okay, so below this price, the conservation of family labor by soybeans matters. The return to soybeans is dominant. And when you hit this threshold of 260, between 260 and 262, we get this split between corn and soybeans. And so you plant some soybeans to conserve family labor, right? You have this labor resource, and the only way to get more labor is to pay $6 an hour for it. And so you get this one little neighborhood here where that family labor constraint has some play. We know it has a very small small shadow value. It's like 40 cents, and so that's why it only has a small effect right here. If we had a larger shadow price for labor, we would have a larger gap right here, where any conservation of labor matters. And then once you hit 263, the gross margin again takes over. Corn is now this dominant activity, and you switch all the way over to 600 acres. Okay, so you get this supply schedule. What do you do with it? Well, you could take the exact schedule as it exists up here. Let's say you had another model, a multi-year planning model for this farm or for several farms or a representative farm, and you wanted to consider policy changes. Well, this supply schedule would be perfectly valid for that, right? What's the effective price of corn? Well, it needs to be relative to some other price, so you need the soybean price as well. But relative to that other price, these are the schedules. These are the planning recommendations that come out of this linear programming model. You could also, if you wanted to really think about sort of what a summary function looks like, try some kind of linear fit through these 3 points. Right? There's no problem putting a trend line through that and getting a slope of a supply schedule. That would be true, especially if you wanted to consider the fact that we are not considering the full set of constraints that live on this farm. We are not thinking about all the possible options that they have, corn versus soybean in rotation, or a corn-corn rotation. Right? So there's a big sort of activity set that we are sort of ignoring that may generate a bunch of these little small things. And so if we thought this was a decent summary of sort of the big picture, then we might fit a linear segment through that and take the supply function to be some linear function there. It's certainly what we do in econometric exercises, statistical exercises, to return the corn supply function. So we could try it here. Okay, but I want to keep going and think about, in our model, that price-quantity relationship that figure 4.1 is showing is an all-else constant, a ceteris paribus assumption for the supply function. Just like if we were doing statistical analysis, you would set the soybean price, the land allotment, all of these things at their sort of base values, or at their average historical values. Whatever you do, if you draw a supply function, that supply prediction from the supply function is an all else constant picture. So, but we have a model here, and we have lots of sort of levers we could play with. What if the soybean price changed, or the land supply changed, or the price of hired labor changed? Any of those changes generate potential adjustments to our supply schedule. And in fact, we have a map right here that tells us how likely, right, from these constraints, from this sensitivity information for any of the pricing, we know how likely it is to generate a change in the supply schedule. So looking at the soybean price, if it increases by 1 cent, right, or falls by 6 cents, then we expect a change to the corn supply schedule, because there's no way to change the soybean level, right? This is telling you how much these prices can change without changing the bushels production of soybeans. Well, the bushel production of soybeans only change if the acreage production of soybeans changes, and the acreage production of soybeans change only must be countered against a corn change, because there's only 600 acres. We are constrained by land. So we are actually seeing right here that these are the price changes that would cause us to shift the corn supply curve we just built. If we had the constraints down here, you would see that the land constraint could also generate changes. For the hired labor, you see here that you need a very large change in the price for hired labor, and so it's not really worth checking. Okay, so any of these could show up as a shift to our supply function. So the range of these variables tell us how much the parameter can change. If we're trying to generate a supply function or trying to think about corn supply for this producer in sort of an analysis context, how much do we get, how much play do we have in that soybean price before we shift our supply function? Well, between 628 and 637. So we could run those simulations. And so I did a couple of those. So I just changed the the soybean price to 628 and the soybean price to 630. Actually, I believe this is 635. Yep. So these labels are bad. Sorry about that. So this is the base. Let me check. Yeah. So the base price 635 and a reduction of more than 6 cents will guarantee us a change. So 628. So I've got the labels wrong there. This is about the 5th time I've had to make changes to this lecture, so I'm not going to fix this one. So this is 635, ignore what's there in the slide, and this is 628. And so what we see here is the normal corn supply function that we just built with an assumption of 635. And what happens if the soybean price falls? Well, you get that shift. So ignore this line too. The soybean price fell by 7 cents, and we get a downward shift. When the soybean price falls, we get a downward shift in the corn supply function. So it takes less price, right? At lower prices of corn, do we get the same supply schedule, right? So that makes sense, because the soybean price is falling. We now require only a lower corn price to produce the same supply amount, because in relative terms, the soybean price falling means we require less return from the corn crop to get that. The one thing that I really wanted to just show, though, is that the quantity pattern is exactly the same. These are two different versions, a shifted supply schedule, but the quantity values are all the same, and that's really because what we call in linear programming, just like a straight line, typically you get a parallel shift, where we get a parallel shift here of the picture of the supply curve. So a parallel shift down, so instead of 260, it's now 257. Instead of 263 or 262, it's now 259. And so you shift this down sort of parallel to each of these line segments, just like you would think of doing in a sort of straight line linear supply model. And that's because the basis, or this basic solutions, the set of basic solutions that satisfy the constraints didn't really adjust. We are just changing the level curve of the revenue line, right? The objective equation, sort of weighting of activities by returns, is adjusting, but the constraints aren't really changing. And so they're still satisfied by the same sort of mixes, and those mixes are sort of live in what we call the basis. So the basis of an LP is the set of corner points that satisfy the constraints. And so as long as we're not changing the right-hand side values of constraints, we're not changing the basis. So we expect to repeat the same solutions over and over. And so basis is a term that used to be a regular feature of linear programming training. As you can see in our textbook, we don't talk about it too much, and this is probably the first time I've really mentioned it a lot. It comes from sort of simplex training, but basis, is just the set of corner points that a simplex algorithm would go and check against everything else. It's the set of sort of corners that satisfy all the constraints simultaneously. And then you choose among basis points by the objective equation rating or weight on the returns. So thinking about basis then, recall from two variable problems, the one thing we do know, the more constraints you have, the more chances you have to generate new corners. There's more chances you have to generate intersections between constraints that make a new sort of edge of the feasible space. And those potentially are alternative solutions if we start adjusting the prices or the coefficients of the objective equation. Thus, you could always get an idea of how many points you possibly could generate for your supply, your demand function, other economic function, just by looking at the number of resource requirement constraints. And so in our model, if we went back to the Tableau, all the way back here, we really just have three resource limits in this model. We have land, family labor, and hired labor. And so those are really the three possible edges that we can make in this model, and one of them is zeroed out. We are not hiring any labor, and so it makes perfect sense that the competition here is a two-activity competition. It's between corn and soybeans, and the basis is always going to reflect that, and you're really going to be able to only switch the basis by whether that labor constraint is important or whether it's not. And so I showed you this, and I said the labor constraint is in play right here, and it is. You're sort of tilting around that corner, right? In the two variable construction of this, it's like tilting the objective equation around that labor corner point until you go to an all soybean or all corn solution. All soybean, all corn. Okay, so the mechanics of this model, while including a lot of sort of distinct stages of production, the mechanics simplify down to a pretty simple look at the comparison of when is labor sort of important in determining the adjustments and when isn't it, right? Because then you're just switching between the more valuable crop to use on your land. Okay, so corn production acres versus the price per bushel. That's what this supply curve is drawn as, and here's how they put the supply schedule together. And I think it's fine. I think it looks nice, and these are two representations of the same thing. And again, I just want to remind you, we could use this supply function in any model, right, where we believe the base assumptions, are going to hold constant with the soybean price, the amount of land in production, those sort of things. And the key, just like any supply function that we would draw for parametric programming, is these are the optimal response, right? So these are the price changes that occur, and this is the best choice of supply. 0, 354, 600. As the price increases, the adjustment to the best choice is what's changing. And that's what we want to feature. That's the sort of story that any supply function tells. It's the result of an optimizing producer making changes, right, as the price adjusts or relative prices adjust. You could do the same thing. We can do the same sort of thing in terms of parametric programming for right-hand side parameter changes. So here the key is to hold all the prices constant and change only one right-hand side at a time. And the interpretation becomes a little different because you're changing now a quantity that the firm demands. Okay, so the firm, through its activities and through its desire to make returns, has a demand for land. Okay, and so the land is capped at 600 under the base model, but there's no reason to say what happens if you expand the right-hand side of the planted land, the land planting constraint. And then the pricing that we would want would be the dual variable of the shadow price. So you would record the shadow prices in response, and so we're getting sort of a reverse of the objective coefficient model for parametric programming. Here we're going to change the quantities and record the price changes. Okay, so it's an input-demand relationship, and you see that they did the same exact solution here. So from 0 to 561, the land shadow price is 171. In this small range right here, the labor constraint starts to play a bigger role, and you get a 169 to 42. And then here, the expansion moves out as far as it can, and then you run out of labor in this model, right? And so there's no expansion. Doesn't matter. 1019.6 is the most you can ever plant, assuming the labor right-hand side values stay the same. Okay, and so you're basically tracking here the land price. What's the demand? As the price falls, you want more and more land. And so assuming this is a valid measure of the rental rate, this is what we were doing. This is what we're looking at. And so, this would be a relevant sort of a rental construction, the land demand by the firm under appropriate assumptions about what the rental supply looks like in the market. This would be their schedule for wanting to rent land. It would also be an appropriate model for looking at when they choose to rent their land into the market versus producing on their land, since it's tied directly to their demand, right? The firm demand may be constrained by a market that has sort of a higher valuation of land than they do. Okay, so I'd like to use the rest of our time to think about taking the spreadsheet model, and I've already made my case for why I think building a Tableau and a spreadsheet is useful and building it to completion. But I want to think about now, if we want to do a lot of experiments, we know that a coding environment lets us change lots of parameters, run it all at once, and then go back and look at a broad set of solutions. Or if we were in a situation like this and didn't just have a few basis points, let me go back here, didn't just have a few basis points, but let's assume we had 24 constraints and they generated something like 10 corners. Well, these prices would be changing a lot. And in a spreadsheet, that means you would be solving the base model, then finding a new solution, looking at the sensitivity information, finding the new price change that you want to do, finding another price change, finding another price change, right? So there'd be a dozen times you'd have to do this, and that would be relatively exhausting. And so when you have lots of basis changes, lots of potential for basis changes, a coding environment would be optimal because you could just go in and just put together a bunch of experiments, record all the values at once, and get the supply schedule that looks like this right out of the endpoint, right? You don't even need to know the sensitivity information. Just set it up, right? It's computing power is essentially zero cost these days. So just increment the prices. Say start at $2 and increment them by 5 cents over and over and over until you get to some maximum price, $2.75, $3.15, whatever. Record all the solutions and then go back and you could trim down the experiment setup to make it more to your liking to present the full supply curve. But you could sort of span the price space quite conveniently there without having to sort of do this detailed work in a spreadsheet that requires your sort of hand manipulation. Or I should acknowledge this because more and more people are better at Microsoft work coming through, coming up through your age group, or the sort of people here. Visual Basic obviously lets you code things and give instructions to an Excel setup over and over. I just don't have any experience with it, so it's possible that you could run a bunch of repeated solutions in Excel quite conveniently as well, but we're training in GAMS, so that's what we'll do. Okay, so let's think about GAMS for larger models. This would be the biggest model we put in GAMS yet, and so we should think about how we might go about doing it. I'm going to argue that we should just go with the classic Tableau representation. Okay, so the Tableau representation converted to an equation setup says let the activities be sort of indexed by I, then let Ci be the objective coefficients, Xi are the choice variables, again indexed over I. Aij is what we call the A matrix. Okay, it's the conversion of activities to constraints. So J is the set of constraints. And then let B sub J be all of the right-hand side coefficients. And then you can compactly write the linear program letting Z be the objective. Z is equal to the sum of coefficients times the activity level, subject to, for all J, there's J of these constraints. Sorry, I didn't put the for all J at the right-hand side here. Summing over the I, the activity level of Aij, and it looks like I also forgot, that's worth editing. Oops. Here. So I left off this, Xi. And while we're here, let's just go. Okay. So the sum of the activity, the A matrix times the activity levels. So the summation here takes away the I's, and then you're left with just a comparison that it has to be less than or equal to the right-hand side B sub J. And we have one of those for every J in the model. Okay, so if we're going to put that in GAMS, well, we can use I or J, but I want to use something a little bit more descriptive for the sets. And so the starting point is always to build out your sets. And so the sets I want, well, I guess the true starting point is reviewing the Tableau setup. So let me pull my spreadsheet back up. And so the Tableau setup had activities up here, right, with these labels, and constraints here with these labels. And so what I really need is I want to build this table, this A matrix right here. This is sort of the classic Tableau A matrix. I want to have a set of columns that have these labels and a set of constraints or rows that have these labels. And so that's how I'm going to define my sets in Excel. And so let me come back to my Excel, and you'll see that I have indeed set up a large set. It's called ACT for all activities in the model, and it has all of those listings, all of those labels. And then for the constraints for the rows, sometimes people use rows here. I just use B and D for boundaries, all the constraint boundaries in the model. So some of those are 0, some of those are physical limits. And so I just gave names to all of these that are sort of close to what was in the Tableau: plant, family, labor, transfer CB, transfer SB, transfer WB, right? So these are all of the constraints in the order that I built them into the Tableau. Okay, and so here I can put the right-hand side values in. I can build a parameter that's B, right? That's going to be B sub J is what I normally call it, but here I'm going to call it B sub B and D because it's going to operate over this set. Okay, so the set, these are the elements of the set, and these are the actual values for the parameter. So when it's plant, let it be 600, family labor 1700, hired labor 900, and all the rest are these transfer right-hand sides, they're going to be 0. For the activities, we need to set up the C, this is C sub I, or in this case, C for all the activities. This is the objective coefficient. And so we just list all of the activities here. So plowing, disking, planting, harvesting, etc. So we have all the cost of activities here, and then the returns for the bushels that we can sell. And then the A matrix then doesn't include the objective equation, it just includes all the constraint coefficients. And so across the top I have all of my activities, ACT, and down the side I have all of my boundaries or my constraints, B and D. And so this is the exact same Tableau that we put in Excel, and it's the simplest method, right? Because you want to be careful, you want to build something step by step, and a spreadsheet lets you test out the setup, especially when you have so many transfer rows and balance equations in these models, and you need to be sure the negative one matches up correctly with everything. And right, we tested it. Remember, we put a 1 in the activity cell for selling corn. We were able to track it all the way back to plowing, which is what we need to be able to do, because that's the theory, that's the production theory of our model in stages. And so we were able to do all that and able to build all that back out. And so doing that first in Excel to sort of understand the logic, complete the theory, and then just transfer that A matrix wholesale into GAMS is, I think, sort of an appropriate strategy, especially as you're beginning. Because if you start and say, well, I have 2 sort of land prep activities, let's make a set for those, and let's build up the matrix for those. Well, you need all of this. You need all of these pieces that are here. You don't need these transfers or the hired labor, but you need those. You need the plowing and the disking row and these 2. And then let's build the planting activities as their own sort of matrix. Well, you need all the ones that have numbers here. And then you end up trying to embed all of these together and make them coordinate. It's much easier to build the big Tableau, confirm it works, and then you can go back and build the thing that will allow you to go in and change your assumption for how much labor is used by planting in these, or how much the yields are. And that's what we're going to finish out our lecture on here. Okay, so that's my that's my sort of argument for these. And so let's open the let me switch out to my GAMS model and show you that in the GAMS IDE here. And so you have this model. It's Chapter 4 Kaiser-Messer form model, Chapter 4 K&M. The sets I've given you here in lines 7 to 10, so the activities and the bind and the boundaries. Ignore these sets for the time being. And then you move down here and you have the table. Right? This table is the A matrix with the boundaries here, the activities here, and then those parameters I already showed you, the right-hand side values. Down here we have to declare the variables. So we have X, right, are the activity levels. R, I didn't use Z for some reason, but R is the return for the farm. The only positive variable, this is our non-negativity declaration, is all the X, right? And remember, you don't need the set identifier here. If you've already declared the variable here, when you call it a positive variable, you just say X. And then we need our equations defined. And so I'm going to call the equations right-hand side for the boundary equations. You can call them anything. Just call them EQN. I don't care. The B and D set, right? We need one of those equations for each of that, and then we need an objective equation. And then remember, the equation definitions in GAMS require put the label and then put ... and then define the equation. And so you can see here I had the correct version of the equation written. So the sum over all the activities, A matrix times X, less than or equal to B sub boundary, right, or B sub J. The objective equation, just multiply C times X for every activity. And that'll solve, right? That gets us ready to use a model statement and a solve statement. And you see I have some other stuff here that we're going to talk about in between. So the model statement says use all the equations. The solve statement says maximize that, declare the objective variable that you want to maximize, and then use LP to do it. Okay, so let's go back to the PowerPoint for just a little bit. So we ended up here, and then we got down here and said let's run some experiments. So we have the GAMS model ready to run. You could verify it running the base assumption, and the base assumption was set up there to run like this. And so you can see here use an assignment to change the price assumption. So actually this isn't a change, but I just wanted to remember you can take use any line in the model to redeclare the parameter value. So even though it was initially set up right here, the C value for HSC was 260, you can use an assignment statement, C and then parentheses HSC, and it'll reassign in that vector C, it'll reassign the one element to be $2.60. And so that's not really a reassignment, it's just me putting that there to be sure that I understand that this experiment is under a price of $2.60, so that when I come down here and reassign that price to be $2.70, I'll have documented that this model goes with a $2.60 price, this model goes with a $2.70 price. And so that reassignment of parameter lets you code and document your full experimental design, right? So the one thing GAMS does require you to do is give a new model name every time you make a change or every time you resolve. And so this would be 4 and 4.1, or if you actually look in the code, this is this cutout is from a prior iteration of the model. Experiment 1, the price is corn 260, and that's going to be called KMCH42. That's the base model. Experiment 2, price for corn is 270. KMCH, this is Kaiser Messer Chapter 4, the third trial. And so that's when we increase the price from the base model. Yeah, and so we could compare those results directly. So at the base prices, the harvested acres for corn is 354, 246. That's the same solution we've been getting. And then when the price goes up to 270, we switch. No more production, no more harvesting of soybeans, only of corn. Okay, and so we've seen that. So we can look at those solutions by going up into, this is from the listing file. You can go through there and find the variable results and see that X prints out this table. Or we could, to compare the results, we just create a parameter to record the results of interest every time that we run a new scenario. And so we are interested in collecting that information. We want to know the crop acreages as we change the price of corn. We have 3 experiments, 3 basis changes for corn. And so we could build a set that is just those 3 harvest activities. Okay, so if we're only interested in what it looks like to harvest, or sorry, in a set, a subset, essentially, that's what we're talking about here. A small selection out of the full set of activities that is about harvested crop acreage, then we could build that. GAMS allows you to do subsets, right? So we have the full set of activities that make up this large row, right? These are all of the activities. And if we wanted to focus on just these 3, the harvested corn, soybean, and wheat acreages, then we can do that, and we would want to build a subset. So ACT is the full set of activities. These 3 are the acreage harvested. And so we could build a subset that is only a small part of the superset, right, the parent set, ACT. And so the syntax in that is pretty easy in GAMS. You just declare the subset using a set statement, and be sure to put the parentheses of its parent set, or the superset, right here. And then you just give the element list that you want to be part of that subset. So here's how it looks. Set, and I'm going to call the new set crop acre. It's a subset, and then just be sure to declare it with these parentheses as a subset of ACT. And then anytime you're using the large set of activities, this subset will make a call and pull out information from that larger value. That larger, any parameter that's defined over ACT will now have a definition for crop acre as well. And you give it these elements. And if you screw up and you don't get the right elements listed here, or they're in the wrong order compared to the superset, GAMS will give you an error, and you have to go back and fix it until you get it just right. They need to be in the same order and have the same elements that can be found in ACT. Okay, so we define that as a subset, and then what I'm going to do is I'm going to make a new sort of junk set, right, just for this. So trial 1 versus trial 2 versus trial 3, I'll just set that up as a new set that says this is experiment 1, experiment 2, experiment 3. And then I want to make a new parameter here that says I want to collect my solutions as something called acres reported, right? Or the new I'm going to report acreage out of each of my trials, and the rows of that parameter are going to be trials, the rows will be trials, and the columns are going to be those crop acres, right? It's going to be the 3 different crops that I harvest acreage on. And so then when we run our trials, we run our simulation, I'm going to use that assignment. I'm going to change the price of corn to $2.50, solve the model, and then acreage report for trial 1, all crop acres, so corn, soybeans, and wheat is going to collect x.l of crop acre. Okay, so it's going to give me the x.l value out of all the activities. It's only going to tell me the levels of the 3 that I'm interested in, the 3 from this subset. Okay, so this is what we were talking about, what the value of subsets are. X, the variable, has there's an X for every activity, but we only want to use the 3 that are in our subset, and so we don't have to go back and redeclare some new variable that only works for the subset. It automatically works. Okay, and so that's what we're after here. So we collect that. It's going to record the level into the first line, trial 1, do a change the corn price to $2.60, run a new model statement, solve statement, and now down here in trial 2 of this new parameter, we're going to collect the updated values of x.l, but only for crop acre. And so you see trial 1 reported here, trial 2 reported here, and there's not enough space to get trial 3, but it finished out and solved there. And so we have all that. And so let me switch out to my GAMS so I can show you where that is. Up here in the sets, you can see I've generated my set declarations here, and that's the full supersets, activities and boundaries. And then down here I created 2 new subsets. Crop acres are a subset of the activities, and transfer yields is a subset of the boundaries. Okay, and so what we just did was we made a subset here that only looked at, within activities, only the 3 harvest activity acreages. So what I'm doing here is I'm pulling off a set of the equations, and I'm calling it transfer yields, and because what I really want to play with are the assumptions on yields. And so it's going to collect XFERCB, the transfer from corn to bushels, the transfer from soybean to bushels, and the transfer from wheat to bushels. And so I want this subset is like going into this full set, right? These are all the boundaries are in the column, but I want it to only be these, right? So it's like pulling on these 3. Anything in these 3 rows I want to be able to play with separately. I want to go in and be able to make changes to these yield assumptions, and so that's going to be our next sort of setup experiment. Okay, so we got our subsets described here. One subset works on this one subset works on this one, and so if we had something that was defined over crop acres and these transfer rows, it would allow us to go in and play with these three yield assumptions. And that's what we're going to do. Okay, so let's assume that I want to completely update the yield assumptions. Let's say that we became more productive. We bought some kind of equipment, and it's a capital purchase, so it doesn't really show up in our variable costs, but everything goes up by 10%. We're just better at producing on the land now. So certainly one option would be just to go back to the activities. Way back here, and you could just go through and manually update these yields. You'd want to be careful to be sure that you are making them more negative, because the yield here is -1. The parameter here is -1 times the actual yield, and you can make those all 10% more yield, but you'd have to do it by hand, and you would lose the information. You wouldn't be documenting your experiment. And so what we want to do is think about how can we do this with a subset. So 1.1 multiplied by all the yield information in the model. This is a non-specific productivity change. And so I already set this up for you and showed you both of these subsets. So we just carve out the rows and columns that hold the yield information. We already made the subset for crop acres. Make this second one that works on the transfer yields, and it's going to isolate those. And so you could write something like this that says, let's code in a yield update. So let's make a new parameter, and that parameter only works for transfer yield and crop acres. Okay, and so let's define that yield to be transfer yield and crop acre, right? So that's the left-hand side. And it's just going to be 1.1 times whatever sits in the A matrix at the intersection of transfer yield and crop acre. So where those three rows and those three columns intersect, you end up with a matrix that's really just a diagonal matrix. It looks like this. And now I'm just saying make that 10% larger, 1.1 times the A matrix value, and then I displayed it displayed the yield, this parameter, and this is what it looks like. So we've got -148.5, I think that's 13.5 more yield than 135, and so everything looks like it's working out. This single multiplier gave us all those changes we need, and so now, because the A matrix, because we have this subset parameter defined yield that translates to just this small piece of the A matrix, those rows, those columns, then we could actually just say redefine the A matrix using that small part of the A matrix, using this new yields we've calculated, using this diagonal matrix, right? With these three things that also are in the A matrix, these three things are also in the A matrix. Take those and just swap those in for that value you have, and we would have to do that with a coding statement. And actually, yeah, let's just skip ahead. So that statement is not shown here, but if we did that, replace the A matrix, you basically just put A matrix x for yield is equal to yield x for yield, right? So just move this to the left-hand side and make it be reassigned to be that. You'll get all these new things in the new solution. And so we run through with our updated yields, and we see that we've changed the price basis relationship. So our trials were 250, 260, and 270 before, and so now at the updated yields, 250 corn gives us only soybeans, 260, 270 give us only corn. Right? So we've lost that sort of these new productivity levels, 10% more times the price, 10% more times the price, have shifted our supply trials away. So we either have to go back and refine these supply trials to try to sort out where the basis change might occur. We could go to a spreadsheet and find the exact sensitivity, since we know this is a pretty small basis problem, or you could just spec it out and say, I want to run 30 trials. It doesn't take much more time to run 30 than it does to run 3, and just try every penny in between there and see if we can find all those values. But it could be the case, the reason I really wanted to play with this a little bit is to think about, what if there were different yield updates? What if the efficiency gain wasn't uniform? Instead, I wanted corn to be 5% more, wheat 15% more, and soybean none. So what if we had some kind of capital investment that made us much more efficient at nitrogen application, and it gave us the biggest boost in wheat, the way we plant, and a little bit less in a sort of row crop situation. So how could we implement this? Well, instead of using a constant multiplier 1.1, we could actually just create a vector and say, okay, when it's corn, it's 1.05, for soybeans, it's 1.0, and when it's wheat, it's 1.15. We can just build a new parameter in GAMS. Just call it yield update over crop acre, and then multiply it by the A matrix for transfer yield times crop acre. Okay, and so here's how that would look in and this is the final piece that's in the code you have. So the parameter yield is still created. We have a new yield update parameter, and this is the one, instead of that 1.1, used to be 1.1 written right here, instead of that 1.1, we're going to make what we call the yield update parameter. It operates only over crop acre, and it lets you go in and set the exact values you want. 1.05 for corn, 1 for soybeans, and 1.15 for wheat. And then you just go in and say, multiply the yield update times the A matrix. That's the new yield. And then if you work through this, you would see that down here, right before we run any models, we take that yield value, right, that's being updated with that yield. This is our sort of trigger, or our simulation parameter, to give us new yields. Take that yield update, multiply it by the A matrix, and then down here redefine the A matrix based on this yield assumption. Now you may ask, why didn't you just put, if this is the same as this, then why didn't you just put A matrix on the left hand side here? Well, it's certainly a valid way to do it. I like to document these kind of steps, and so when I'm using things, sometimes if it's an experimental setup, I'll build a new parameter, so I always know that I can track back without having to look at the same thing on the left hand side and right hand side. And so that's just a personal preference. Everything else though will follow through the same, right? Except instead of getting a 1.1 change to all the yields, you'll get a 1.05, 1.00, and 1.5. Run through that and look at this. So we run 250, 260, and 270, and we've increased yields disproportionately in wheat. Corn had a yield increase, but the basis found a new sort of home, right? So we changed the returns to wheat enough through improved productivity that now our trial definitions, 250, 260, and 270, this is all for the corn price. Say, if the corn price is too low, you're a wheat producer. If the corn price improves, you're going to shift a lot of this over to corn, but not as much, but not all of it. And then when the price gets high enough, you'll shift it all over there. So that labor constraint is still controlling this sort of neighborhood when you do both of these, that higher labor constraint. But it may be the case, it may be the case that this is a new corner point that we haven't found before, because we've never been in a situation where we were actually rotating the corn versus wheat price. We've always been rotating the corn versus soybean price when we looked at the previous examples. And so we found a new basis point at these new yield values. Okay, so there's lots of things going on. What if we don't have the right prices? Well, we're going to save that for our next lab period coding example, where I'll show you how to efficiently run just a ton of experiments at once using a loop and recording all the values. And so it makes it so that you don't have to sit there and cut and paste all of those. But we'll save that off for the next one. With that, I am right at 75 minutes, so I'm going to shut this down, and you can move on and look at your assignment now.